Hello, we're now ready to talk about the reflection and scattering of ultrasound by structures in the tissues. I've already mentioned these are particularly important because these are the mechanisms that give rise to echoes, and the echoes are the information used to create the ultrasound image. The term reflection refers to what happens when ultrasound is incident on a smooth surface. This is exactly the same as when light hits a smooth surface like a mirror or a sheet of glass or metal. Some of the energy is reflected. And so when ultrasound strikes a smooth surface in the body, for example the capsule of the kidney or a blood vessel wall, something of that sort, some of the ultrasound energy is reflected and the rest of the energy travels through that tissue into the deeper tissues. So we have partial reflection, some of the energy being reflected, the remainder passing through into the deeper tissues. Now, an important fundamental law of physics is that energy can't be created or destroyed, and so we know that this is true when the ultrasound hits this interface. So if, for example, 1% of the energy was reflected, we would know that 99% of the energy must be travelling through to the deeper tissues. If 10% was reflected, 90% would be travelling further into the deeper tissues. Now let's look at a particular situation. What I'm showing here is perpendicular incidence, which is the particular situation where the beam is hitting this tissue at 90 degrees. This is the situation that you often want to achieve from a clinical point of view because it provides the maximum accuracy in measurements, for example. So we'll start with this and then later talk about the more general situation. Now, what I'm showing is the ultrasound traveling from the probe, striking that tissue interface. Some of the ultrasound travels through the interface into the deeper tissues. The rest is reflected back to the probe, and the machine will detect that and view it as an image, as an echo, and place it in the image. Now I've labelled a specific property of the tissues, Z1 and Z2. This property is known as the acoustic impedance, and it characterises the acoustic properties of different tissues. Down the bottom I show the definition of the acoustic impedance. It's the product of two tissue properties, ρ and C. Now ρ stands for the density of the tissue, so that's the weight per unit volume. For example, the weight of 1 cubic centimetre of tissue. C is the propagation speed of ultrasound in the tissue, which we've already seen and talked about before. So you take the density, multiply by the propagation speed, and you get something called the acoustic impedance, and the units of that are called rails, which is named after the great British physicist Lord Rayleigh. So if two tissues are different, then in general they will have different acoustic impedance values. Here is the definition of something called the reflection coefficient. This is a measure of the fraction of the ultrasound energy that is reflected at a tissue interface. Formally, it's defined as the intensity of the reflected ultrasound divided by the intensity of the original beam that struck the tissue interface. So we've got if this number was 0.2, for example, it would mean that 20% of the energy has been reflected. We calculate the value of the reflection coefficient, as I've shown here. We take the difference between the two acoustic impedance values, so the acoustic impedance values of the first and the second tissue, and square it. We divide that by the sum of the two values, also squared. Now there's a couple of things to say about this. The first one is that if I interchange Z1 and Z2, I would still get the same number because things are squared. So it doesn't matter whether the tissue is going, whether the ultrasound is travelling through the first tissue and then into the second, or whether it's coming the other direction, coming from the second and into the first tissue. The reflection coefficient will be exactly the same. Another thing to say is that we are dividing like by like, and therefore the units will cancel out, and this will be a pure number. And indeed it will be a number between 0 and 1, since it represents the fraction of the energy that is going to be reflected. Next thing to notice is that if the two tissues happen to have the same value of acoustic impedance, in other words, if Z1 is equal to Z2, then the top line of this equation is 0. So that then tells us the reflection coefficient is 0, which means no energy is reflected. This slide shows that situation. So if we have the first and second tissues having the same acoustic impedance, so if they're identical from an acoustic point of view, there will be no reflection. The ultrasound will pass straight through that tissue interface. There'll be no echo from it. We won't see it in the ultrasound image. So, for example, if you had some kind of a tissue dividing two parts of the liver, but the actual tissue either side of that was the same in terms of its acoustic properties, so that Z1 and Z2 were equal, there would be no reflection from the interface. Here's the exact opposite of that situation. If we have a very big difference between the two acoustic impedance values, then essentially all of the energy is reflected. Now, this isn't so easy to see when you look at the equation, but if you try it, you'll find out it's true. So if you, for example, try to calculate the reflection coefficient where one of the acoustic impedance values is 100 times the other, you'll find that the reflection coefficient is almost 1, which means that almost all of the energy is being reflected. What are typical interfaces in clinical experience where this is true? Well, the best known and most common would be when you've got an interface between soft tissue and bone, or soft tissue and air. So when you have ultrasound travelling through soft tissue and striking bone, you know that virtually all of the energy will be reflected. Similarly, when ultrasound travels through soft tissue and then strikes air-filled lung, for example, again, you'll expect all of the energy to be reflected. Now let's look at the situation where we are not at perpendicular incidence. So the tissue interface is now sloped at some other angle relative to the ultrasound beam. Now what I've shown here is that I have drawn a reference line, the black dotted line, at 90 degrees to the tissue interface. And I'm going to be using that as a reference line. I'm then going to define two angles relative to that line. So I've got the incident angle, which is the angle between the incident ultrasound beam and the reference line. So that's theta I. And then I have the reflected angle, which is the angle between the reflected beam and, again, that same reference line. And so that's theta R. And the law of reflection for ultrasound is exactly the same as it is for light. And that simply is that the theta I is equal to theta R. In other words, the incident angle is equal to the reflection angle. Now, because this is exactly the same as the reflection of light, we use a term for it. We call it specular reflection. So you'll often hear when people are talking about ultrasound images and the physics of ultrasound, they talk about specular reflection, which simply means that the reflection obeys this rule, that the incident angle is equal to the reflected angle. Now, from a practical point of view, this means that when the ultrasound strikes an angled interface like this, the reflected ultrasound is going off somewhere else. It's not returning to the probe, and therefore it won't be seen in the image as an echo. That information is lost. So when we look at a sloping tissue interface like this, we will not see echoes. So that's probably enough to give you an idea about reflection. Let me now talk about scattering. Scattering is sort of the complement to reflection. Scattering is what the term we use when ultrasound strikes very small objects. By small, I mean small relative to the wavelength of the ultrasound. So we could think of very small structures within soft tissue, for example, capillaries and lymph vessels and things of that sort, but also other kinds of functional structures. We can also think in terms of very small gas bubbles. In both cases, they behave as scatterers. And what this means is that a small fraction of the energy that strikes an object, and now if you'd like to look at my diagram, you'll see I've just represented one scatterer as a red dot. When the ultrasound hits that, a very small amount of energy is sprayed in all directions. So it's quite different to reflection. With reflection, the reflected ultrasound goes in one specific direction. With scattering, it goes in all directions. So this means that we will always get some small fraction of the scattered energy directed back towards the probe, and it can be detected and displayed in the image. So reflection is very sensitive to the orientation of the tissue interface. Scattering is not directional. With scattering, it doesn't matter what direction we look at a scatterer from, we're always going to get an echo from it. Now, in a moment, I'll be showing you an example ultrasound image, and it shows you that most of the echoes in a typical ultrasound image come from scattering. There are relatively few echoes within the image that come from the reflection from tissue interfaces. So scattering is the most important part of image formation. Therefore, it's important to understand the nature of the scattered echoes. You can think of there being thousands of scatterers that are all interacting with the beam at the same time, and the scattered echoes from those go back independently to the probe, where they are then combined together electronically by the machine. There's a randomness to this process because of the fact that the scatterers are randomly distributed within the tissues, and therefore we get an interference pattern, a random interference pattern that we call speckle. This liver image is an example of soft tissue being imaged by virtue of the scattering from the fine structures within the soft tissue. So it's all the structures within the liver that are producing this speckled grey appearance, which we recognize as typical soft tissue appearance for an ultrasound image. Now, this random dot pattern of varying shades of grey is what is referred to as speckle. It's not an actual representation of individual scatterers, and that's important to understand. It is an interference pattern, and so it is not directly related to the fine structure of the liver. You can actually get a clue to this if you look very carefully at this image. Close to the skin surface, we see a much finer speckle pattern. If I then go much deeper in, near the diaphragm, towards the bottom of the image, you can see that the speckle pattern is much coarser. This is because of the differences in the beam shape and pattern of the ultrasound beam, close up and deeper in. So what we're seeing is that the speckle pattern is in fact really an artifact, an image artifact, but a very useful one because it allows us to see soft tissue. Now, while the speckle pattern of the soft tissue is not in itself meaningful, the average intensity is meaningful because it represents a genuine tissue property. If I have abnormal tissues within the liver, as I think we probably do in this case, then you'll see different brightness at some points. And that's genuine. That tells you that those tissues have different scattering properties. Commonly, increased scattering properties may be related to fibrous degeneration, fatty infiltration, or other processes of that sort. So in summary, I've shown you that reflection is what happens when ultrasound strikes surfaces. We only get echoes that are detected and displayed in the image when the beam is perpendicular to that tissue surface within the body, and we call that perpendicular incidence. When the tissue is angled relative to the beam at some other angle, the reflected energy goes away somewhere else and it's not detected by the probe and therefore not displayed in the image. The strength of the echo that comes back when we are in that perpendicular situation depends on the acoustic impedance difference between the two tissues, the tissue before the interface and the tissue after the interface. And when that difference is small, we get a weak echo. When there's a large difference in the acoustic impedance, we get a much stronger echo. When we have something dramatic like a soft tissue air interface or soft tissue bone interface, we get essentially all of the energy reflected and none will go through into the deeper tissues. Scattering is a different process entirely, and that's what happens when ultrasound strikes very small objects, very small structures. It's independent of angle, so we're always going to see scattering, and scattering typically is the way we image soft tissue. The one thing that I've explained is that scattering causes speckle, which is that grainy appearance, which is typical of ultrasound images. Now that can be distracting to your eyes when you're looking for subtle variations in echo strength. And for that reason, we'll see later on, the manufacturers have introduced a couple of different techniques to try to reduce speckle so that it is less distracting to your eye.